Regan hadn't really traveled a lot before this, but for her internship, she actually found the contact and went to Xray in India. And you probably saw some of her pictures in the Aggie Agenda, and had a very interesting experience both in Germany and in India that she can talk about with you today. So, Regan, please.
Hi guys, like you said, I'm Regan. Talk to you about working for Xray. I was there for 5 months. Right before, I was in Germany for a month working for a company called Fraunhofer. And my project was developing mobile sensors for the estimation of grain qualities. Okay, so a little introduction. The main question of this project was, how can we fight malnutrition in developing countries? We can do that with biofortification, developing cultivars with higher nutrient concentrations in those countries. Currently, breeders are using wet lab analysis. It's costly, so it's not really feasible for those countries. It's very time consuming. You have to harvest, tenure, stuff off, wait for the data to come back. Also, as most of y'all know, it takes years sometimes to develop new cultivars, and farmers in these countries are not going to adopt them unless they bring them a higher market price, even though they're healthier. And so using Xray fluorescence technology could be a solution to this. So Xray fluorescence right now is most commonly used in the mining industry. It measures the concentrations of certain elements in a sample. So this graph basically shows, so when you measure a sample, it gives you a spectral data like this, energy versus the count. So it will give you, each element has its own kiloelectron voltage energy, and the counts, however many times that number is repeated, like how many times it's picked up by the sensor, it'll show you that. So how it works, basically, once you put a sample in there, it's hit with X-rays, the sample gets excited, it shoots out an electron from the inner shell of an atom, and then an atom from the outer shell, an electron from the outer shell will drop down in that place. And when it does, it releases an energy in the form of K alpha. And the intensity of the energy released is directly proportional to the concentration of the elements in whatever sample you measured. So here's just this periodic table shows you my project. We were specifically looking for calcium, iron, and zinc. And you can see like the K alpha for calcium is 3.6, iron 6.4, zinc 8.6. Each one has their own specific value. And in the future, we hope to be looking for toxins, not just nutrients, so like cadmium and arsenic. So for this project, we used 750 rice samples that came from Erie, grown in Los Baños in the Philippines. In 2018, we had 2 sets of data, one from the dry season and one from the wet season. We used the hold and behold samples or the same sample, hold and behold. The machine we used to measure was this Oxford Instruments Exapine 8000. And for every different type of measurement you want to do, you have to have your own method put into this machine. The Harvest Plus office there at Xray developed the method that I was using. That's the one it was. And so to start, this was a very new project at Xray. I was really like the first person to ever really work on it. So they wanted me to develop kind of a standard operating procedure. So I took about 30 samples and measured them 5 grams, 10 grams, and 15 grams. And this Oxford machine gives you the data in milligrams per kilogram or parts per million of whatever element you're looking at. And so the 15 grams showed a stronger correlation, so I decided to go with 15 grams for measurements. So we started, after we did all that, we kind of all met and decided that the best way to do this, we needed to dry the samples. It's very humid in India. So we left them in a 55 degrees Celsius oven overnight, and then we took 10 grams of each sample with the holes on, measured the weight and the volume. The reason we took 10 grams of the whole is because 15 grams wouldn't fit in those little cups, so couldn't have that much. Measured each sample 3 times. Then the samples were dehulled, rinsed with distilled water, dried them again. Then we took 15 grams, recorded the weight and the volume, measured them 3 times again. And then we took the CSV files produced from the spectral data, which I'll explain in a second. The reason we measured them 3 times is because when I was testing it at the beginning, after the 5th time, or excuse me, after the 3rd time, the standard variance did not significantly improve, so we just decided 3 times was good, just for the sake of saving time. So this shows the relationship between the hulled and dehulled samples. And again, this is just about 30 samples, so not a whole lot of data here. As you can see, there's not much of a relationship whatsoever with the hulled samples between iron and zinc, but in dehulled, it doesn't look so bad. And I did notice within the same sample, once you take the hulls off and measure it again, the zinc values are almost double, and we don't really know why that is. Like, do the hulls block some of the X-rays? We don't really know. So this shows zinc, the relationship in zinc between hulled and dehulled rice, because we also want to get a reliable relationship between the hulled and dehulled samples, because it will also save us time. For example, the breeder won't have to, harvest everything, take it, dehull it, then measure it. Also, the breeder could go out in this field, like if we can make these handheld sensors, harvest just a few plants from this plot, measure it. If it's looking really bad, you can say, okay, we know for sure we don't want this, can just decide not to harvest that at all and save even more time. So going back to the taking those CSV files, we used an R script that was written by the people I worked with in Fraunhofer. And basically how it works is when you take those files off of the Oxford machine, there's 2 files for each sample. So one is recorded at a higher intensity of X-ray and one is at a lower intensity. And so with the 3, we repeated the measure 3 times. So it takes the higher intensity, you can measure iron and zinc, and then it takes the lower intensity to determine calcium, because calcium is just much more visible on the spectrum with a lower intensity X-ray. And this is the exact same sample, hulled and dehulled. And so this is iron and then zinc and calcium. The reason iron, the graph, doesn't look super great is because iron is at a much lower concentration in rice. And so we're thinking maybe the sensors just aren't really, they're not really able to pick up that data really accurately because it's such a small number. And so here, this is hulled rice and dehulled rice, and this is the relationship between the values that the Oxford machine gave us, so milligrams per kilogram, and then these numbers are what the R script gave us, which is the area underneath the curve of each of those for each element. And so we really want this to have a really reliable relationship, because once we make these handheld sensors, we want them, we want to kind of be able to program them in a way that is like 100% accurate. So that's the reason we want to compare all this data together. So future applications for this, fine-tuning of the sensors, of course, which is going to require more testing. Because right now, for irons and calcium, whatever you want to measure, measures it in parts per million. And like I mentioned before, cadmium and arsenic to measure toxins, those elements are going to be in parts per billion. And right now, these sensors are not able to detect that. We want them to be durable, mobile, so we take them out in the field. Making calibrations for other crops, so sorghum, millet, peanut, maize, whatever you want to measure, there's no reason why you can't, but again, you'll have to make your own calibration for those machines. Making these sensors available to the buyers is a big thing. So ICRSAT is also wanting in the future when these are developed, they want to get involved with the government over in India. So when the buyers go to buy grain in large quantities from these farmers, right now they just say, okay, this is how much I'm going to give you for your crop, and take it or leave it. So they want it to where these buyers will have these sensors. They can go measure someone's grain and say, oh, you have your crop is higher in nutrients, so we're going to give you more money for your crop. So it will also give the farmers an incentive to grow healthier crops, which is back to the biofortification thing. So I would like to thank the team at ICRSAT, the team at Fraunhofer, and especially Dr. Murray for kind of pushing me to go all the way to India for this. And then some pictures from traveling.
So, got two questions. I'm not really familiar with the technology, but is it currently being used in other crops? I know you mentioned making calibrations in the future, but is it being used in other
Yes,
crops?
so the Harvest Plus office there at ICRSAT, they're working with millet right now, millet and sorghum.
And then the second one is this technology, like what would it cost? Is there a price to it yet?
Yes, it's pretty expensive.
I mean, I assume it's really pricey. But
Yeah.
Have you considered using like an additional calibration of looking at the soil concentration of zinc and iron? Because I know that, especially with trace elements like zinc, you can have quite a bit of variation in a short space.
Mhm.
Soil concentration that might help your calibration.
That is a good point. So this project is like the very, very beginning. And so that's not something that they've looked at yet, but it's definitely something they probably should look at.
So I don't know much about rice, but why are you looking specifically for arsenic at rice?
Yes, it's a toxin in rice that I know arsenic for sure is like can be a problem in rice for sure.
Do you know how far the X-rays penetrate? Try, just wondering if it's graded whole, but can you try a milk sample of rice, Roundup sample?
So I do know the Harvest Plus officer, they were testing grinding up rice before they measured it to see if that made a difference. And I don't know what the outcome of that was.
So I don't know what the safety implications are, but our plant breeders gonna have to walk around with us like that non-penetrative vest that you get at the dentist.
No,
X-rays.
no. So well, when it's handheld, that's actually a good question. I don't really know, but the big benchtop machines that we use now, it's a closed system, and you don't have to worry about any of the radiation from that.
We still have 3 more speakers, so we should probably get ready to